so remember, a function was just a special kind of rule, right, where each input has exactly one output, right? And we learned the vertical line test for telling whether a graph was the graph of a function. We said each x can have only one y. That's the definition of a function. Each x, only one y. Each input, only one output. And we started to talk about domain and range of a relation or a function last class. But today we're going to talk about domain and range, trying to find domain and range just by looking at a graph rather than looking at a list of points. Okay. So here's a graph of y equals f of x. The entire graph is shown here, so it's not like those things keep going. There aren't any arrows there, they just stop. And we want to know the domain and the range. So if the domain is the set of all inputs, or the set of all x values that that function lives on, its domain is this interval of x's. All of those x's have y values defined by the function. Okay, and then the range is the set of all y values created by the function. So the range is this guy. So the range is that set of y values that the function lives on. All right, so here's an example of a function. We want to find its domain and its range. So to find the domain, you look along the x-axis to find inputs that correspond to points on the graph. So we're looking for what x values does this function live on. -7 to infinity. The smallest x value it lives on is -7. And then it just keeps going to the right forever. So it's -7 to infinity. We'll include the -7 because it's a closed dot. And we never include infinity. So we're going to write our answers in interval notation here. All right, and then the range, to find the range, look along the y-axis and find all the outputs that correspond to points on the graph. Okay, so what's the smallest y value that this function has? It's -2. Yeah, so the smallest it is -2, and we'll include it. And then what's the biggest y value that this function has? It goes to infinity, yeah, because of this arrow pointing upwards. So -2 to infinity is the range of that function. All right, so you guys try a little practice. Identify the domain and the range of each of these graphs. Okay, so here's my function. When I talk about domain, I'm talking about just x values. What x values does this function live on? What's the smallest one? -5. And then it goes all the way up until the biggest one, which is 3. So I put -5, 3. Should I include those endpoints? Yes, because they're closed dots on those points. So I put square brackets. And then the range is the y values that the function lives on. Smallest y to biggest y. So what's the smallest y here? 0. Biggest y? 4. Should I include them both? Yep. Yes, you always do smallest to biggest when you're using interval notation. I don't know what you mean by starting point. Oh, because that's the furthest left? No, yeah. So when you're writing an interval, whether you're describing x's or y's, you always put the smaller on the left, bigger on the right. So like when you're reading range, you should read bottom up, like down, lowest to biggest. Okay, so for the domain of this one, smallest x is -4, and the biggest x is 5. So I do -4, 5. And I have an open circle at that -4 x value, so I'm going to put a parenthesis there. And I have a closed circle at 5, 0, so I put a square bracket there. And then the range, smallest y to biggest y, that's -5 to 5, not included, included. Okay, and then the last one, smallest x to biggest x. So my smallest x is -4. My biggest x goes to infinity because that thing just keeps going down and to the right. So I'll include the -4, never the infinity. And then my range, what's the smallest y value for this function? -infinity. It just keeps getting more and more negative. So we put -infinity on the left because you always put the smaller on the left. And then the biggest y value for this function is 0. And I'll include the 0. Yep, because a negative number is always smaller than 0. Yep. Yeah, it can get confusing because in magnitude, like you can have a really big negative number, but we think of that. Sometimes you think of it as a really big negative, and sometimes you think of it as a really small number. Yeah. Okay, so we did some of this in the activity last class. If I want to find f of 0, this was the function notation that we just introduced. If you remember, this does not mean f times 0. It means whatever's in parentheses there is an x value, and it's asking you for the y value. Okay, so when x is 0, what is the y value of this function? 3, based on the picture, yeah. So f of 0, you write equals 3. So for what values of x is f of x equal to 0? So what numbers can I put in parentheses there that give me y values of 0 on my graph? -3 and 2. Because f of -3 equals 0 and f of 2 equals 0. -3 and 2 are called the zeros of the function f because they're the x values that make the function value 0. So we call them zeros. The real zeros are what we have called up until today x-intercepts. And starting today, we can use those words interchangeably. X-intercept, 0 of a function. So remember the definition of a function said each x can have at most one y, right? So how many x-intercepts can a function have? As many as it wants. You could have infinite, right? In this picture, it had 2, right? You could have a function that is just a horizontal line on the x-axis, right? So I could draw a function that just looks like this. That's a function. It passes the vertical line test, and it has infinite x-intercepts. Okay? So we can have as many as we want. But how many y-intercepts can you have? 1. Because if you're going to pass the vertical line test, the y-axis counts as one of those vertical lines. You can only have one y-intercept, or the vertical line test will fail. Right? So if I have a graph and there's 2 y-intercepts, vertical line test says it's not a function. Okay, so we can describe the behavior of a graph using these 3 words: increasing, decreasing, and constant. Every graph tells a story, and you usually tell that story from left to right. Okay? Just like we would when we write intervals and when we have number lines, we generally read everything from left to right. Okay, so let's look at this, this story. This is time, temperature, flu scenario. So we have hours after 8 a.m. and then we have temperature, right, of someone who has the flu. So over what open interval is temperature decreasing? So this graph represents a person's temperature. On what time interval is their temperature going down? 5 hours? Not per hour, just in what time, in what hours was it going down? From 8 to 11, yeah, from hour 0 to hour 3. Hour 0 to hour 3, the function was decreasing. Temperature was going down. Okay, so I would write 0 to 3 as the interval of time that temperature was decreasing. I used open brackets because they asked me for an open interval. Because the question is, what is happening at 3, right? After 3, the temperature starts going back up, right? So at 3, should we describe that as it's decreasing or it's increasing? Right at 3. It's neither. So we don't include the 3 in the description of where it's increasing or decreasing. So we're saying the temperature f of x falls as time x increases from 0 to 3. So as time goes forward, temperature is going down. All right, so now I want an open interval on which temperature is increasing. 3 to 5. And again, I'm not going to include the endpoints. They asked me for an open interval. And when we describe increasing and decreasing, you always use an open interval because the point where it changes from increasing to decreasing, we call that a relative extreme point. And it's kind of doing neither at that point, right? Neither increasing nor decreasing, so you don't include it. All right, over what open interval is the temperature remaining constant? Yep, 5 to 7. Temperature is constant at 100 degrees. So as time increases from hour 5 to hour 7, temperature is not changing, staying constant. What time is temperature at its lowest? T equals 3 or 11 a.m. Yeah. Or I guess we're calling this X. X equals 3 or 11 a.m. because X equals 3 corresponds to 3 hours after 8 a.m. So this temperature flu scenario illustrates that the ideas of when a graph is increasing, decreasing, and constant are fairly intuitive. You can read a graph from left to right. If the graph is going uphill, it's increasing. If the graph is going downhill, it's decreasing, right? Downhill, decreasing, uphill, increasing, flat, constant. You always read it from left to right. And you always describe where increasing, decreasing, and constant is happening by using x intervals. Okay, so you only give the x. Okay, so a more precise algebraic definition says that if on this interval, I'm not even going to go through this. Skip that. You got it. Okay, so let's move on to relative maxima and relative minima. When a function changes from increasing to decreasing, we say that the function has a relative maximum, right? So look at this first picture here. Function's increasing, increasing, increasing until it hits x equals c, and then it starts decreasing. So we call that point a relative maximum at x equals c. So c is the location of the maximum. The function value, the y-coordinate of that point, is f of c, and we call that the maximum value, right? So c is the location, f of c is the maximum. And similarly, if a function changes from decreasing to increasing, like in picture 2, decreasing, 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 and then it turns around and changes to increasing, we call that a relative minimum at x equals c. So c is the location of the minimum. The value of the minimum is the y-coordinate. Okay, so I want you to answer some questions about this graph F here. Domain, range, zeros. I'll come around and ask and help if you have questions. So we're going to use the graph of F to answer all of these questions. Use interval notation whenever it's applicable. So I would like to know the domain of f, all the x values that this function lives on. What do you think? Negative infinity to infinity. Because these guys have arrows that indicate they go down and out forever. So this is always going to continue to move left. This one's always going to continue to move right. So my domain's going to be negative infinity to infinity. How about the range, the y values that this function lives on? Negative infinity to 4. Should I include the 4? Yes. All right, the zeros of f. That's synonymous with x-intercepts, right? So what are the zeros? Negative 4 and 4. F of 0, right? That 0 is in parentheses. Does that mean it's an x or a y? It's an x. So when x is 0, what's the y on the graph? 1. When x is 0, y is 1. Good. All right, the intervals on which f is increasing. So again, you read from left to right, and we identify uphill spots. Okay, so let's see. Before I start trying to describe them with intervals, I'm just going to highlight, right? So here I'm uphill, 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 and then it starts going downhill, so I'm going to skip that. And then here I'm uphill, and then it starts going downhill. So those pink areas, I want to describe them by telling you what x values those areas are on. So this first one, what's the smallest x for that first highlighted piece there? Negative infinity, and where should I stop? Negative 2. You always give the x value. Gotcha. Negative infinity to negative 2. And I'm not going to include the endpoint. You never include the endpoint when you're describing increasing and decreasing. Because right at negative 2, it's doing neither, right? Right after negative 2, it's going to go to decreasing. All right, so how about the next interval that's highlighted here? What are the x values there? 0 to 3. Okay. 0 to 3. So remember from one of our early classes, we described that with a union, 0 to 3. So you just do a big capital U. Union, think of like marrying those two sets together. All right, intervals on which f is decreasing. So this time we're reading left to right and we're looking for downhill areas. So that would be this spot here. And what x interval is that? Negative 2 to 0. And then this spot here is 3 to infinity, because we're describing x, so we're going to the right. So that's going to keep going till infinity. Always looking for the x value. Yeah, when I ask for intervals on which, there's an implicitly written x intervals on which. Because, that's a great question. Why do we always use x? Because the definition of a function means that if you know x, you know y, right? So I only ever have to tell you x, and you can get all the information you need by using the function rule. But if I tell you y, sometimes there are two y's that go with an x, so it's ambiguous, like that whole thing about the heights and the basketball players. So if I just give you the y coordinate, sometimes you won't know which one I'm talking about. But if I only give x, you know exactly where I'm describing on the function. Does that make sense? Okay. Okay, so values of x. So I'm looking for an interval of x values. Maybe an interval, maybe it's just a list, I don't know. For which f of x, which you could read as y, right? F of x represents y coordinates, are bigger than or equal to 0. So I'm looking for points on this graph that have positive y coordinates. Okay, so where are they? from x goes from -4 to 4. So this whole section of the graph right here that I'm highlighting, all of those points have positive y coordinates, right? Because they're above the x-axis, positive y coordinates. So if I want to explain where those points are using just x values, I would say from -4 to 4. So I would put -4, comma 4. Should I include the endpoints there, the -4 and the 4? Yes, why? Or equal to, right? Because f of x equals 0 at those points. Yeah, if this had said just greater than, I would not include the -4 and the 4, right? Because I would want strictly positive values, but it would be 0 at -4 and 4, which is not positive. Okay, relative maxima and the numbers at which they occur. Okay. So do I have any relative high points? Any places where the function changes from increasing to decreasing? Yep, we've got one right here. That's a relative max. Yes, you can. Are there any others? 3, 2. Yeah. That's also a relative max. So the way we defined a relative max was any place where the function switches from increasing to decreasing, place where it turns around from increasing to decreasing. So we have 2 of them. And that word max can be a little bit misleading because it might make you think the biggest point on the graph. Same thing with min, it might make you think we're looking for the smallest point. But the reason we use relative or local, both of those words are used to describe this, is because if you look in its own little neighborhood, right, just draw a little neighborhood around that point, now it's the highest point in its neighborhood. Think of it like a mountain chain, right? Sometimes when you go climb a mountain, you might summit 4 peaks in a day, right? One of them is the highest, but you've actually hit 4 different peaks. Right? So this guy is also a peak. Or it's not the highest one, but it is a peak. Okay, so the way we describe these things, we would say we have a relative max of 4, right? The maximum value is 4. And it occurs at -2. And then I should put another sentence here to describe the other one. I also have a relative maximum of 2, and it occurs at 3. So max of 2 occurs at 3. All right, and do we have any relative minimum values? We do. Yeah. So you might have been tempted to say there aren't any because the graph keeps going down forever. So there is no global minimum because you can't ever get to the bottom. But we do have one local minimum because if you just look at its little neighborhood, it's a low point. And so the local minimum value is 1 and it occurs at 0. Okay, values of x for which f of x equals 3. -3 and -1. So if f of x equals 3, that means y equals 3. That's the same thing, right? F of x is just a new fancy way of writing y. So I'm just going to draw a line at y equals 3. Right? This is the line y equals 3. And it intersects my graph in 2 places, -1 and -3. So those are the 2 x values that make f of x equal 3. That make sense? Okay. All right, so is f of 5 positive or negative? Negative, yeah. So we go over to x equals 5 because that 5 is in parentheses. It means it's an x value. So we go over to x equals 5. We go down to the graph. F of 5 means the y value here. And even though we can't tell exactly what it is because we've left the graph, we know it's negative because why? How do I know it's negative? Because what? Because the quadrant we're in, yeah, we're below the x-axis. Yeah, so we know it's negative. So this is mostly just lots of new notation to describe stuff that we can see in a graph. Right? So we have one last little topic for today, even and odd functions. So we call an even function. We have a special name for functions that are symmetric about the y-axis, which we call even, right? So if you could take the graph and fold it along the y-axis, if the y-axis acts like a mirror, right, one half would lay on top of the other, we call any function that has that property an even function. So I wonder why we call that even. Any ideas? Seems like a funny choice for some to describe that kind of symmetry. Do you guys all know what the graph of y equals x squared looks like? Looks like that, right? Is that even? Yeah. And so that's y equals x squared. It's even because it has y-axis symmetry. Would that exponent on the x, is that an even or an odd number? Even. Yeah. That's why. It has to do with the exponents. Yeah. Functions. There are functions that are even that don't have exponents, right? Like y equals the absolute value of x. Right? There's no exponent there, or you could think of it as a 1 exponent, which doesn't make any sense with the word even, but these are sort of the classic examples of functions that have even symmetry, that have y-axis symmetry. So that's why we named that kind of symmetry even. So the way, yes, go ahead. Oh, if you have a more complicated equation, it's a great question. So maybe you can guess. This thing I'm going to call even. This is neither. And then odd functions would be like so what do you notice about the exponents in this first one? All even. Exponents in this last one, all are odd. So the one in the middle, there's some of each. You can't classify it as even or odd. This rule only works for polynomials, right? So if you wanted to think about, say, the absolute value of x, you can't apply this rule, right? This only works for polynomials. But it's a handy little shortcut. So algebraically, the way you check to see if something is even is if you plug in an x value, you'd get some y value, right? If you plug in that same x value, but the negative version, right? Like maybe this was 5. If you plug in -5, you're going to get the same y value as when you plug in the positive, right? So if I plug in 2.5, I get -14.44, which is the same thing I get as if I plug in -2.5. So that's how you tell if something is even. If a positive x and a negative x give the same y value. So the way we write that with all our brand new function notation says if you plug in an x and you plug in a negative x, you get the same thing. this is the algebraic definition of an even function. It's always the case if the function's even. Yeah. Okay, so now we have an odd function. Odd is the name that we have decided to give to functions that have this property where they have symmetry that if you folded the graph over the x and the y, so fold it like into quarters, right? Fold it over x, then fold it over y. This piece in the upper right would lie right on top of this piece in the lower left. Okay. So that's a special kind of symmetry that we call origin symmetry, and we call it an odd function. And x cubed is kind of the classic example of an odd function. Looks like that. If you folded it over x and then over y, those two pieces would match up. And that exponent of 3 is why we call this kind of symmetry odd. Okay, so the algebraic way to recognize an odd function, right? We can recognize it graphically by recognizing the symmetry. The algebraic way would be if you plug in an x value and get a y, right? If you were to plug in the negative x, you wouldn't get the same y like you do in an even function, but this y value, right, whatever that number is related to this number how? To the negative, or the opposite, yeah. So this guy is the opposite of this guy. So what we would say here is if you plug in an x and you plug in a negative x, you don't get the same thing, right? This one would be negative and this one would be positive, or vice versa. One of these is positive and one of these is negative. So what we do is we throw a negative right here. If you take the opposite of that one, then they would be the same. Take the opposite of one of them and then they're the same. So that is the algebraic definition of an odd function. Any function that's odd will always have this property. Right, yeah. So like let's look at the pictures, this picture that I have here. So if I plug in 1.28, my point, you can hardly see it, 1.28 is 12.13, right? And this point here, if I plug in negative 1.28, my output is negative 12.13, right? So the y values aren't the same, they're opposites, right? So f of x represents the y value for x, f of negative x represents the y value for negative x. They're not the same, so I can't put an equal sign there, but if I take the opposite of one of them, they would be the same, right? So if I took the opposite of this guy, I would have 12.113, and that would be the same. Okay? Okay. So let's see, maybe I'll just write it one more time. So if I had negative 12.13 and 12.13, those are my two y values. The only way I could put an equal sign between them, I can't right now because they're not equal, right, is if I threw a negative sign in front of that one. Now it says negative, negative, and they're equal. Yep, yep. That negative right here, you should generally, in fact, it's a good idea to get in the habit of saying, instead of negative, saying the opposite of. Yeah. So now I'm taking the opposite of negative 12.13.